All right, so thanks for everybody for joining in. Welcome. And today we have Rodrigo from Chile. He's our first speaker from the Southern Hemisphere on our channel. And we are very happy that he's going to talk now about Einstein-AdS gravity from conformal gravity.
Okay. Thank you very much, Ian. Thank you also for the invitation. It's certainly a pleasure to be here and to be able to give this talk. It's not entirely a review. It contains some recent results we have just put on archive like a month ago. So in a certain moment, I will try to be constructive. I mean, to review some of the main issues and to be slightly pedagogic for simplicity, because it's very complicated at the moment. It's very technical, but I will always try to provide the simplest examples available. So what is this title? We're trying to make connections between the concept of renormalized action for AdS gravity as coming from taking certain conditions on the general structure of conformal gravity. At least we will provide the example of 6 dimensions. But before that, I will tell you a little about my motivation. My motivations is within the framework of AdS-CFT duality. What I have in mind is always holographic properties of Einstein-AdS gravity. In particular, I would refer to an alternative renormalization scheme that we have developed not so recently. This is an old story with new results. It's not a typo in that line. There is counterterms with a K that I will explain what I refer to. Also, I will try to stress the appearance of conformal-like or pseudo-conformal structures, mostly in the bulk form of the gravitation action. And this is mostly due to the fact that it's the appearance of the Weyl tensor for Einstein space. And I will make connection. I will try to make a brief connection, because at the end of the day, in the talk, I didn't want to make a very extensive talk. So I would mention briefly the concept of renormalized volume in the mathematical context, in the mathematical literature. And I will briefly comment on the connection between renormalized volume with the concept of renormalized area in 2 dimensions lower, which is of relevance in the computation of holographic entanglement entropy. So this is a very old story that everyone should know, so I will mention briefly. This is in the context of holographic renormalization. This is how to extract physical information from the conformal boundary, that means the conformal infinity, which is defined by asymptotically AdS spacetimes. So we know that the quantities that you can define in the boundary CFT are related in a precise prescription by this formula, very well-known formula, where the gravity side is evaluated in the classical limit of gravity. So this field phi, you have to take a precise prescription as you approach to the conformal boundary, and of course defining in order to define a source, which is the one that appears also in the field theory side. In a more concrete way, in order to describe asymptotically AdS spaces, it's very convenient to describe them in terms of this Pfefferman-Graham form of the metric, which makes manifest the conformal structure at the boundary. Why? Because I will tell you the ingredients of this expansion. The boundary of the spacetimes is located, it's a spatial boundary, is located at z equal to 0. That's the reason why this form of the metric is making evident the double pole at the boundary of asymptotically ADS spacetimes. And at the same time, this G metric accepts a power series expansion in the holographic coordinate. This Z is the holographic coordinate, this is the radial coordinate. And as you can see, in Einstein gravity, you consider only the even powers in the Z coordinate. And of course, depending on the dimension, you will arrive to a certain coefficient that is the one that corresponds to the holographic stress tensor, and is the one that cannot be fully determined by the equation of motion. So the idea of holographic renormalization or holographic reconstruction of the spacetime is to provide certain boundary data, like G0 metric at the conformal infinity, and to be able to order by order reconstruct the metric, reconstruct all these coefficients in terms of covariant functionals of the G0 metric. So this is a very well-defined systematic procedure. And then you realize that both at the level of the action or at the level of the variation of the action, you have divergent terms, because as you could see, as you approach to the boundary, as you approach to the asymptotic region, there will be divergences in the Z coordinate. In order to cancel the divergent terms, the addition of some local counterterms, local in the sense that they depend on the boundary metric and the boundary curvature, and essentially intrinsic quantities of the boundary, the addition of these counterterms is required in order to deal with the regularity of the action and the variation of the action. In order to extract holographic information from the gravity theory. So you can understand the different terms in this action, as the first term is the Gibbons-Hawking term. This is necessary to define a Dirichlet problem for the metric. What you define when you add the Gibbons-Hawking term, what you define is the canonical momentum. Is the one that sets the problem in a similar fashion as in classical mechanics. Because the Einstein-Hilbert action is actually a Lagrangian. From the classical mechanics point of view, you could think of the Einstein-Hilbert Lagrangian like a Lagrangian that depends linearly on the acceleration. So you have to get rid of high derivative terms. So if you have the Gibbons-Hawking term, you are doing that, getting rid of acceleration terms. And what you define is the structure at the boundary of the type, the canonical momentum by variations of the metric. It's of the type P delta Q in classical mechanics. So if you have the canonical momentum, this can be supplemented in order to get something which is renormalized, because it's not enough to define finite quantities at the boundary. You need the extra counterterms in order to render this quantity, the quasi-local stress, the Brown-York stress tensor. You have to render it finite, and by the addition of counterterms, you take functional derivative with respect to the metric and define an extra part of the canonical momentum, of the stress tensor in order to cancel divergences. So by a suitable rescaling of this Brown-York stress tensor, you define holographic quantities in terms of the G0 metric. This contains holographic information like the well-known computation of Weyl anomaly. And so that's the reason why this procedure is defined in this way to be able to extract holographic information at the boundary of asymptotically AdS spaces. What is the general form of this? As I commented, it's a very well-defined procedure. It doesn't mean that it's that easy, because as you go out in the dimension, go up in the dimension, it becomes more complicated. For instance, for low enough dimensions, it's enough to add one or a couple of counterterms. These are power counting argument, so you know exactly how many counterterms you need according to the dimension. And these cubic counterterms, maybe they are required already in 8 dimensions or so. So what I would like to emphasize here is the fact that I want to emphasize a couple of features of this procedure. First of all, I would like to stress the fact that the renormalized Brown-York stress tensor, because it's defined in terms of the canonical momentum, is linear in the extrinsic curvature. And the rest of the terms are coming from counterterms, which are local functions at the boundary. That means intrinsic terms. There are no quadratic, for instance, terms in the extrinsic curvature. And the other things I wanted to stress is the fact that there is no general expression for an arbitrary dimension, that possibly would reveal some extra features of the gravitational action that maybe you would like to identify. And of course, this procedure is far more difficult to be carried out in higher curvature or higher derivative gravity theories. So even though it's systematic, in practice, it's very technically involved, and there is no general answer in any dimension. So I will take this as a motivation in order to try to present, it's not so new, but to try to introduce for the ones that are not familiar with, an alternative procedure to this construction. So I will try to motivate this introduction of an alternative renormalization scheme. This is mostly based on a few observations. What I presented this far, it was the way people were dealing with holographic renormalization in the very beginning. After that, around 2004, 2005, in a series of papers, mostly by Papadimitrou and Skenderis, they were emphasizing the fact that a Dirichlet boundary condition for the full metric doesn't really make sense in asymptotically AdS spaces. Why? Because if you take the Fefferman-Graham form of the boundary metric, you notice that it's divergent actually. And the only thing that you can keep fixed at the boundary actually is prescribed by the gauge gravity duality. You want to keep fixed the metric, the G0 metric, because it's the source of the holographic reconstruction of the spacetime from the boundary into the bulk. And if you try to fix the G0 metric, of course you will produce a divergent term because of the contribution as in the holographic coordinate. So, but anyway, they were able to reformulate. I mean, they were able to connect two things that looked like separated. If you try to define a well-posed variational principle to to keep G0 metric fixed at the boundary, actually you end up needing counterterms in order to renormalize the divergent terms that appear in the variation of the action. So in this way, these two problems, the one of regularity of the action or variation of the action, and the variational problem defined in terms of the conformal structure at the boundary, they are connected. They are not separated, like I was presenting originally somehow. So the key point, maybe the key point of this talk is a naive observation, is the following fact. If you have a look on the Pfefferman-Graham expansion of the extrinsic curvature, you will notice that essentially it's of the same type. The leading order in the extrinsic curvature is of the same type as the leading order in the expansion of the metric. So in a way, there is no difference of varying the metric, the boundary metric, or varying the extrinsic curvature. So in principle, as long as you keep the theory holographic, that means describing the variation of the action in terms of the G0 metric, and as long as the variation of the action is finite, practically adding intrinsic terms or adding extrinsic terms you cannot make difference between these two procedures. So let's provide. This was also emphasized in a recent paper by Weyl. If you think from that point of view, that means that the leading order in the extrinsic curvature is the same as the leading order of the metric at the boundary. They're both well or ill-defined, because if you try to keep one fixed, the only quantity that at the end of the day you need to keep fixed is the G0 metric. Both induce divergences at the level of the variation of the action. So, in principle, you could think of adding counterterms of a different type. Counterterms that contains some certain dependence on the boundary metric, but also some dependence of the extrinsic curvature, because at the end of the day, you want to express all the variation just in terms of the G0 metric at the conformal boundary. So it would be equally well-defined to carry out a different procedure as long as the variation of the action is finite and is holographic. That means expressible in terms of variation of the sources. Because this accident is an accident of asymptotically AdS spacetime.
Yeah, but Rodrigo, I mean, when you say that you're relating K and H from the path integral point of view, it's like a mixed boundary condition, right? And then you have to put in counter terms which do not change that boundary condition. So how does you...
This is of course, at this level, I have not proved anything at all. But at the end of the day, you show that there are, if you add counter terms with the extrinsic curvature, you can produce the same holographic quantities.
Yeah, on shell, yes, but one has to make sure.
No, definitely. Everything is using the equation of motion. It would be impossible to try to. This could correspond to a completely different variational principle. It's an accident of the on-shell form of asymptotically AdS spaces. I'm not making any claim of shell. It would be impossible.
Yeah,
but conceptually.
But the whole point was adding the Biebers-Hawking term was that it could also work off shell, right? I mean, so okay, you're putting in something that, and the usual counter terms respect that given, I mean, the boundary condition of Dirichlet. So here one has to also make sure that the kind of terms that you're putting on, that kind of also
more than on shell or off shell, the difference is where the boundary is located. For everything I will do, my boundary is located in the asymptotic region because there are asymptotic conditions. There are not boundary conditions. because you're right. If you add the Gibbons-Hawkins term, you have a well-posed Dirichlet problem for the metric at any radius. These conditions are asymptotics. They are true only in the asymptotic region.
So your point is essentially that because you are imposing this asymptotic fall of conditions on the path integral, so because of this asymptotic fall of conditions, it will not be a problem. You can actually think of K and H as same as not very different. And so both
in
the
terms
momentum
of the same variables, in terms of the same holographic source.
Mm-hmm. Okay, so you.
But yes, you are definitely right. This is only works in asymptotic. We have discussed this issue in the past as well. Yes, only works in the asymptotic boundary.
Okay.
So let me
Can I ask a naive question?
Yes.
So
yes.
What you wrote in the previous slide, you are putting this counterterms which are functions of both H and K. But you can't do away with H completely. Can't you write everything in terms of just K?
No, because I'm presenting this thing in pedagogical way using this approach. But you will notice that we discover the things in the opposite way. We propose a concrete boundary term, which are related to topological invariants. They are related to topological terms. So we have to understand that. First, we proposed this long time ago in the context of pure gravity. We had no idea it had holographic implications. And it took us long to try to understand what exactly we were doing. Because it seems to be that, as Ayan was saying, the variation problem was not well defined.
Yes.
So because it is, I will review this later, but it is a problem that intrigued us for many years. We didn't have an explanation why you were able to add topological terms to the action, and it worked. I mean, we regulate, for instance, the Euclidean action, the charges that you could define, but actually it looked like contradictory with the variation principle. And the only way you can understand such a thing is that the fact that at the end of the day, there is no such a thing as Dirichlet problem at the conformal boundary.
Thank you.
I will come back to this point definitely.
Thank you.
So the other somehow piece of evidence that I like now, that I realized not so long ago, is the following thing. There is such a concept in asymptotically AdS spacetime called conformal mass. In order to evaluate the mass of a black hole in, let's say, Schwarzschild AdS, you can take the electric part, the Weyl tensor. The Weyl tensor has 4 indices, and you can define a normal to the boundary. So in such a way that leaves 2 indices which are living at the boundary, this I and J, and the normals are essentially the radial direction of the normal to the boundary. So in this way, you define this object, which is the electric part of the Weyl tensor, and in the original prescription in 4 dimensions, Aschenker and Magnon says that you need to evaluate the electric part of the Weyl tensor to get in a codimension 2 surface as a surface integral, and you get the mass of the black hole. This was extended to any dimension and not associated to the addition of any boundary term in the action. This was a proposal extended by Magnon and Das around 2000 that also says that you always have to evaluate the electric part of the Weyl tensor. So what is the electric part of the Weyl tensor compared to this quasi-local stress tensor that they were defined by counterterms? So you will say that the electric part of the Weyl tensor is traceless. So of course, it's different respect to the quasi-local stress tensor. The quasi-local stress tensor contains a trace in in odd dimensions, in all odd Wald dimensions. So of course they cannot be the same, but they differ by the anomaly, by certain terms that produce the anomaly. This was already discussed in the paper by Magnon and Das at the end. For instance, they provide the difference, the explicit difference between quasi-local stress tensor and the electric part of the Weyl. So, in general, the trace of the quasi-local stress tensor will produce the Weyl anomaly that it appears at a holographic order in the expansion metric. So to be concrete, for instance, in 5 dimensions, this is computation that they did. The electric part of the Weyl tensor differs by a quantity whose trace is the anomaly. No surprise, they contain essentially the same type of information because they both provide mass of the black hole, but only one produces the right Weyl anomaly. So I just mentioned this to make the following observation, because if you use the condition of the fact that the Weyl tensor is traceless, you can trade off the electric part of the Weyl tensor by the subtrace of the Weyl tensor. The subtrace means the trace just at the. And notice the following thing, that you can, in Einstein spaces, as I will discuss, I will emphasize this later on, the electric part of the Weyl tensor in an Einstein space, it depends directly on the Riemann tensor, certain contractions of the Riemann tensor. If you use Gauss-Corazzi relations, you end up with an expression which is not linear in the extrinsic curvature, quadratic in the extrinsic. So this is also a piece of evidence of the fact that some of the quantities that you can discuss for asymptotically AdS spaces, they are actually non-linear in the extrinsic curvature. There is no way in the standard procedure, as I show, that is the Brown-York stress tensor is always linear in the extrinsic curvature. So that means that maybe you are able to resum some of the contributions coming from counterterms in terms of the extrinsic curvature, because the expression that I obtain here is quadratic in the extrinsic curvature. This is very puzzling, but it suggests, this is just motivation, it suggests the fact that maybe some of the counterterms can be resummed in terms of the extrinsic curvature.
So Rodrigo, I want to understand something. So this particular relation Tij that you wrote down, is it finite? This thing in the brackets, Rij minus Kijk.
Is the electric part of the Weyl tensor. We have the right fall-off such that the mass, for instance, of the black hole, because the object that is always interesting in all this procedure is the Weyl tensor. This is a key ingredient of the construction. Right. It had the right fall-off. If you integrate the contractions of the Weyl tensor in a codimension 2 surface, you will produce something finite. So
right, and this is also conserved by Bianchi or something.
Yes,
like,
yes.
And so it's a finite object that exists.
Yes.
So this is sort of universal, that this object is.
Yes. The only thing that they are missing is the Weyl anomaly, because
the only thing that misses is the
Weyl anomaly is the holographic order. It comes from the holographic order. Yes. So they don't have a way to see Weyl anomaly. And on top of this, I must stress that it's a prescription that they provided, but it is not associated to the addition of boundary term, any particular boundary term. They just give a formula, but it's not derived from somewhere. Mm-hmm. Okay, so I introduced this in order to motivate to conjecture the appearance of nonlinear terms in the extrinsic curvature at the level of the quasi-local tensor. So maybe there are counterterms which are nonlinear in the extrinsic curvature. And I will provide this prescription that we found in a certain moment. So these counterterms with a K, crazy name that it just came out just to make the difference. They are essentially boundary terms which produce the regularity of the ADS action, but depends on the boundary metric, the extrinsic curvature, and also the intrinsic curvature of the boundary. So this is not surprising. This I didn't invent this object. This is called chain form. The chain form is a Chern-Simons form for the Lorentz group because it contains dependence on the spin connection. At the end of the day, if you project at the boundary with a certain choice of coordinates, you end up with the extrinsic curvature. So this is the chain form at the boundary of 2 n dimensions. And this is, I will explain this, is related to the existence of topological terms of the Euler class.
One can I interrupt? Sorry.
Yes.
So in the previous expression, you had terms which are only quadratic or in extrinsic curvature, but now you're bringing in arbitrary polynomials. So
it's very nonlinear. It's very nonlinear in the extrinsic curvature. But this is a given. This is a given expression. It exists in the literature. You prove at the end of the day.
My question is why you need it if you have. If you showed some universal formula which was only quadratic, which is finite at the boundary, and except it misses the Weyl anomaly, but it seems to work otherwise fine. So why you need this?
No, because at the end of the day, Ashtekar provided this formula, but they didn't say to which boundary term they are associated to, and the only thing. This is associated actually to topological terms. And at the end of the day, you prove that the previous formula is a truncation of what you get from topological terms. And the topological terms, what induce at the boundary is a highly nonlinear polynomial in the extrinsic curvature. There is no other way. This is fixed by the Euler theorem. It's not something I chose to be like that.
So this boundary term, is it purely a topological invariant, the one that you're adding?
No, this is related. I will write down the formula in maybe 2 slides more.
So it's a boundary of a topological invariant.
Because what is a topological invariant is the Euler characteristic.
Yeah, okay. I see.
The Euler characteristic is the difference between the Gauss-Bonnet, let's say Euler or Gauss-Bonnet, and this term at the boundary.
Right. Okay.
All right. So what was more difficult, and I will not refer so much to, the odd-dimensional case is far more difficult because it's not related to anything that we know. There are no topological terms in odd dimensions. So this had to be constructed somehow case by case. And finally, we realized that there was a certain pattern associated to this. It's very much like Chern-Simons form, but this is at the boundary of odd-dimensional case. So this is an even form. So it's not truly a Chern-Simons. I have not found anywhere in the literature something like that, apart from the fact that I will explain something where my knowledge is coming from, why it appears a double integral and these sort of things. Let me explain a little more.
Sorry, so your statement is that this for 2n plus 1, it is not a boundary term of a topological invariant or something like that.
There are no topological terms in odd dimensions. So it shares many features in common with the Chern form, But to be honest, that is like an object that we just invented.
Yeah, but in 5D, you can write versions of Chern-Simons gravity, for example.
Right.
Could it
I
be,
will explain. I will explain something like that. There are actually, whenever you have Chern-Simons forms, Chern-Simons are not truly gauge invariant forms, because if you perform a finite gauge transformation, it will differ by something. So in order to restore gauge invariance, you have to provide a contact term. You can imagine like two Chern-Simons, one living in one part of the space, the other touching each other at the boundary. And this boundary contains a mix of the connections between one Chern-Simons and the other. And this is the typical trick in anomalies that appear. And I took this parametric integration from there.
I see.
So let me explain, try to explain why these parametric integrals and so on. This is everything related to Chern-Simons. Of course, the defining feature of a Chern-Simons is the fact that the exterior derivative of a Chern-Simons is a topological term. It's the trace defined in an algebra of f of the curvature associated to the group to a certain power. So this is truly a topological term. And this, how you construct explicitly the Chern-Simons out of this relation. This is part of the explicit realization of the homotopy operator, and the homotopy operator contains this parametric integral. So you provide an explicit representation of the Chern-Simons in this way in terms of the connection and this interpolating connection. There is an interpolating connection that interpolates between 0 and the corresponding connection. So you end up with this object, which is ft to a certain power, and you recover the standard form of the Chern-Simons densities for any group. So that's the reason why it appears naturally at the boundary of even dimensions. It appears at one parametric integral. Let me explain. And there are global issues. For instance, in the case of Euler, this is what we were discussing exactly. The Euler term, the integral of the Euler term, or Gauss-Bonnet in 4 dimensions, is the Euler characteristic, and there is this boundary correction due to the Chern form. Because what is truly a topological invariant is the Euler characteristic. So let me suggest, this is not quite precise. I mean, I'm being very loose, but I'm trying to just to suggest where this form may come from. If you have an object that is called transgression form, which depends on 2 connections of the group, it's actually defined, it's a truly gauge invariant object. It's sort of extension of Chern-Simons form. And it contains information on 2 connections, A bar and A. And this time you take an interpolation between these 2 connections, between A and A bar. For t equal to 0 is A bar. For t equal to 1 is A. So you take this generalization of Chern-Simons form, and you can prove, this is contained in these old papers by Stora and Zunino and people in the 80s, but a transgression form is actually a Chern-Simons form defined in one connection minus the Chern-Simons form defined in the other connection, plus a contact term. And the contact term, where these 2 Chern-Simons touch each other at the boundary, is something that depends on a double parametric. And this is not exactly the same as what I'm doing, but I'm just suggesting that this type of tricks appears in this context as well. even though I'm not able to exactly relate what I was presenting to this construction, but at least the form is very suggestive.
So here you would suggest that this A bar is something zero, one of this A is non-zero, the other A bar is zero or something like that.
There is a standard construction. I mean, to derive this chain form, there is also a A bar in the chain sinus. It's coming from a product metric. It's something that gets rid of non-tensorial components of the spin connection. It's a typical trick that is in the textbooks. And A bar is actually a spin connection that restores Lorentz invariance at the boundary. Because the problem is the following: whenever you work with Gauss normal coordinates, you can split the spin connection, and there will be components of the spin connection which are not tensor. It's not the extrinsic everything. These components are still a connection at the boundary, so it's not a tensorial expression. And for instance, Eguchi, Gilkey, Hanson, they discussed this issue, that considering a second spin connection in order to restore gauge invariance and also tensorial quantities at the boundary. We can discuss on this issue.
Yeah, just trying to understand. So basically, this would be some sort of A bar which will have a trivial boundary metric.
Yes.
Where you don't anomaly doesn't appear or something like that.
Yes.
And then okay, I see.
It's the only way out that I know. But okay, it's presented in this way, looks slightly difficult. Okay. Let's comment on what is the use of this.
Just one question before that. So is the claim that the boundary term that you have provided that can also account for the Weyl anomaly or not?
Yes.
It can, I see. In arbitrary dimensions and.
It's difficult to prove in arbitrary dimensions, but yes.
In d is equal to 5, yeah, at least in d is equal to 5 and d is equal to 3.
Yes.
Okay. Yes, definitely. Thanks.
So the first evidence that these boundary terms were able to provide regularity for the action, it was the fact that you check black hole thermodynamics. If you check black hole thermodynamics and you evaluate the Euclidean action for Schwarzschild-AdS black hole, for instance, you will get part of the mass coming from the bulk action and the contribution coming from the horizon, which is related to the entropy, and a divergent term as you approach to the boundary, to the infinity. The Euclidean counterterms, what they do is that they provide the extra part that you need for the internal energy to complete the mass. And they cancel identically the divergent term that appears at infinity. And they also provide, in the case of odd dimensions, this is an issue that appears in the context of standard counterterms.
Rodrigo, so sorry, I'm not able to follow. Can you explain this expression again? This limit R goes to infinity.
This is the evaluation on Schwarzschild-AdS of the Einstein bulk action. The Einstein bulk action alone, without Gibbons-Hawking term, provide a fraction of the mass, not the full mass. This is the typical problem of the Komar mass. You provide a fraction of the mass, you provide the right entropy coming from the horizon, and because you are evaluating the full Euclidean action in the volume, you also have in AdS a divergent term. So people, what they do in background subtraction procedure, they subtract the divergence, but the problem is that the problem of the mass, the internal energy remains. People can add the Gibbons-Hawking term and the problem of the mass is corrected. You get the total mass, the full expression for the mass. But here it is clear that if you evaluate this proposal at the boundary in Schwarzschild-AdS black holes, you get the extra missing part of the mass. You get vacuum energy in the odd-dimensional case coming from the boundary terms, and you get a divergent term that cancels the divergence coming from the bulk. Is it clear now?
Yes, thank you. Yeah.
So this was evidence at the level of solution that we have that something was had nice properties related to these counterterms with K prescription. So let's move on. So we were able to provide the correct black hole thermodynamics with a consistent internal energy augmented by the vacuum energy. So how this is related to the question of Ian, how in the world these two prescriptions, the standard one, and this prescription which is non-linear in the extrinsic curvature, how in the world they are the same? They could be the same. So in principle, you don't need the Gibbons-Hawking term to, I mean, in principle, it doesn't appear in this prescription. It's not natural because it's actually coming from a single topological term. So you are adding the chain form and rendering the Euclidean action finite. So how these two prescriptions are related? They're related in this way. You can force the system to behave like the other. So you add and subtract the Gibbons-Hawking term. So you add the Gibbons-Hawking term and you add minus the Gibbons-Hawking term in this last term here, because this delta by this antisymmetric delta is a delta of one index. So it will produce the trace of the extrinsic curvature once again. It's just a fancy way of adding zero. And now you can expand Pfefferman-Graham. You can expand in Pfefferman-Graham the contribution coming from the extrinsic curvature and all the fields in Pfefferman-Graham. You just start collecting, you power expand, collect term order by order the terms, and start identifying them. So here, to simplify the discussion, here I expanded like something that contains no curvature, one curvature, because this is the Schouten tensor of the boundary. It's linear in the intrinsic curvature, plus other terms which might be quadratic in the intrinsic curvature. And when you do that, after a while, you collect terms and you get something that doesn't contain the curvature and something that is linear in the curvature, and so on, so on. This is a simple example. I know what you are going to, you will say that 4 dimensions is too easy. You can do it in an arbitrary dimension. Is actually, there are more arguments provided in this recent paper, and we were able to provide a general comparison between standard counterterms and these counterterms with a K, and at least we provide a matching for conformally flat boundaries. There is a mismatch that I will discuss about later. So,
Rodrigo, can I make a comment here?
Yes.
So essentially your claim is that what you're doing are taking the Einstein-Hilbert action and adding a topological piece to that. And the sum is finite when you take the cutoff to infinity, right?
Yes.
Yes. So I think the point is, suppose even if you put any kind of cutoff, which is, and you use, so this statement is boundary condition invariant, right? It doesn't depend on what boundary condition you're choosing. So essentially, if you can put any finite cutoff and choose whatever boundary condition, you add some kind of add and subtract whatever variational counter term, which will be the analogs of Gibbons-Hawking to that.
Right, right.
And yeah, and then you could define, you can work your prescription for any boundary condition.
Yeah, but the problem of that naturally there appear variations of the extrinsic curvature that you cannot get rid of. This is a real problem that we have to consider any arbitrary boundary. So variations of extrinsic curvature can be mapped into variations of G naught at the conformal boundary, but not necessarily, it's not necessarily true at a finite boundary.
Yeah, but so this is actually what I was thinking, that why should, yeah, I'm a bit confused about this. So if you have added a topological counterterm, right, the total variation, whatever it is, should not matter, right? It should be always changed.
Let me tell, we can discuss this later, but let me anticipate something. I'm not dealing with this problem, but I'm very aware of that. If you add a topological term, you cannot define the Dirichlet problem at the boundary. There is a very well-defined procedure called Meyer's term, which is the generalization of Gibbons-Hawking for any Lovelock term, including Gauss-Bonnet.
Yeah, I know that.
But it fails in the critical dimension. It fails in the moment the Lovelock term is topological. You end up with zero, because the top look at the expression of the canonical momentum in, think of the canonical momentum in 2 dimensions. It's identically zero. So when you add the Gibbons-Hawking term in Einstein-Hilbert, which is topological in 2 dimensions, the canonical momentum that you produce is identically zero in 2 dimensions. The canonical momentum for the Gauss-Bonnet by Meyer's procedure is identically zero. So you cannot define the Dirichlet problem. In the critical dimension, you cannot define. And this is my problem.
I see. Thanks for the explanation. Thanks.
Right. I will try to speed up.
One quick question. This in your prescription, there was no arbitrary parameter, right? So this E naught that you showed in the previous slide in the thermodynamics argument, that is fixed in this approach?
Yeah, it's fixed, but it's arbitrary. So it's conformal data. You can give anything. It's completely arbitrary.
I see. But it seemed like you had no arbitrariness in the term that you wrote. Maybe I missed something.
No, because everything from the point of view of the variation is the variation of the total action is written in terms of variation of G naught. And this is holographic prescription. It matches holographic quantities.
Okay, thanks.
So let me elaborate on something. Let me suggest something. I know that it is very naive. I will try to explore, from now on, I will try to explore a possible connection between topological terms, addition of topological terms, and conformal quantities that may appear in the bulk. Why? Because if you use this Wald prescription, one of the simplest formulas to compute the energy and other conserved quantities is the Wald prescription, the Wald formula. You take the Lagrangian, you take the derivatives with respect to the Riemann tensor, you project in a coordination 2 surface, and you get the mass. The funny thing is that you can trade off this chain form by the Gauss-Bonnet and a topological number, and you can use the Gauss-Bonnet in turn, and at the end of the day, dropping this topological number for a while, you end up with this renormalized action, which is the Einstein-Hilbert action plus the Gauss-Bonnet term with a fixed coupling. This is funny because, in principle, the topological term, there is no way of fixing the coupling from the point of view of the equation of motion, but I have given a consistent picture in order to keep this fixed because of regularity of the action. because of regularity of the Euclidean action, also the charges. Because if you take this action and use the Wald prescription, guess what? You end up with a formula that depends on this combination of terms, the Riemann tensor and some combination of the metric. This is not any quantity. This is called this should be called AdS curvature, because the curvature associated with the Lorentz group is the Riemann tensor, but because you are dealing with the AdS group, this appears augmented by a quantity in terms of the metric, in such a way that F is identically zero, the field strength is identically zero for global AdS, for example, for a space-time that is constant curvature. So it will always appear this quantity that I will refer to AdS curvature, and the other quantity that appears is the Weyl tensor. And the Weyl tensor has this definition, is the Riemann tensor and the Counterterm tensor with the skew symmetric product with the metric. But if you particularize the Weyl tensor for an Einstein space, you plug in this condition of Einstein space, what you end up with is the Weyl tensor for Einstein spaces which have exactly the same form as the AdS curvature. So there are two notions in this game which coincide for Einstein spaces, AdS curvature and Weyl tensor. And so it will play an essential role in what I will review now. So one of the immediate consequences is the fact that if you consider Wald charges plus topological terms in the odd-dimensional case, you are able to prove that the natural definition that appears is the electric part of the Weyl tensor. So it's very simple argument to take topological terms with a fixed coupling and use the Wald prescription, and the formula for the energy that appears are the conformal mass, the electric part of the Weyl tensor. So this is a concrete way of realizing the prescription by Ashtekar, Magnon, and Das. But not enough. This was the Weyl tensor somehow at the boundary, at the level of the charges and so on, is interesting. But also let me re-express this renormalized action in a fancier way. We can put this renormalized action in the following form. Actually, this is the product between curvatures and the metric. So the deltas by the deltas will produce cosmological constant. The deltas by the Riemann tensor will produce the term linear in art, which is Einstein gravity, Einstein term, and the quadratic terms quadratic term in the curvature is the Gauss-Bonnet term. So for a fixed coupling, the action becomes McDowell-Mansouri action, and it was studied already in the literature a long time ago. And this is the form, the most compact form of the renormalized action for AdS gravity. So we proved already. So what we did, we actually did the opposite. We add topological terms, we fixed the coupling, we converted into a Chen form, and we proved that it was the same as the standard counterterms.
But sorry, this equivalence is only on shell, no? Or
yeah, once again. It's holographic renormalization on shell to me. So the funny thing is, I don't know how to call it. I chose to call it pseudo-conformal or conformal-like here. I don't know to what extent I'm being rigorous about it. But I noticed the follow observation that is for Einstein spaces, this quantity is nothing but the Weyl tensor that we had written before. So if you take the explicit contraction, only one term survives, which is the Weyl squared term. So the on shell, as Ayam is correctly pointing out, the value of the action, of the renormalized action, is like pi squared for the Einstein spaces. You will say, okay, it cannot be conformal because conformal gravity is something else. It's a higher derivative gravity theory. Of course, it's not quite the same. This is somehow you should be able to obtain it by taking precise boundary conditions from conformal gravity. This is what I will comment later. So the things that I like from this, slide is the fact that you render somehow trivial the thermodynamics for global ADS. You notice that Euclidean action is identically zero for global ADS. So the Wald charges, because they're proportional to the Weyl tensor, and the entropy as well. So everything is consistent, somehow automatically consistent for global ADS. This is not only a property of 4 dimensions. If you add topological terms in any even dimension and you fix the coupling, this action had some really nice features, really nice properties. For instance, if you play the exactly same game as in 4-dimensional case, you convert this into a polynomial of the curvature, and this antisymmetry is delta, in such a way that this is a polynomial. You can convert it into a polynomial Weyl tensor for Einstein spaces. So it's a general feature of any even dimensional case, the fact that this can be expressed as a polynomial of the Weyl tensor. There is, of course, there is Weyl square, Weyl cube, and so on, so on. It started because there are no traces of the Weyl, of a single Weyl. So this is also the fact that you have a very compact expression for the renormalized action in AdS gravity in even dimensions. But I would like to explore more about this issue of a possible connection between conformal structure, because the Weyl tensor appears is like a polynomial of the Weyl, and maybe shares certain features with the conformal gravity. And the key point is, it was an observation that Maldacena was making. In 2011, he was saying that one can obtain, this was very, it was an argument. It was not explicit. He was not providing an explicit realization of this claim. So he was claiming that if you start from a higher derivative gravity theory, which is in 4 dimensions, is conformal gravity, is Weyl square gravity, and in a higher derivative gravity theory, you have other modes in the Pfefferman-Graham expansion. G1 is a new source because the equation of motion in this case, they are higher derivative gravity theory. It's a higher derivative gravity theory. What you understand is a 4 derivative gravity theory where Einstein spaces are a subset, sort of trivial subset within the conformal gravity theory. So the equation of motion for conformal gravity is the Bach tensor, which are derivatives of the Cotton tensor. The Cotton tensor are derivatives of the Schouten tensor. So Cotton tensor is 3 derivative, Bach is 4 derivative. And you can prove using this form of the equation of motion of the conformal gravity that Einstein spaces are always solution, in 4 dimensions, they are always solution of conformal gravity. Now, because Einstein spaces, they are defined in terms of the Ricci tensor, so the Schouten tensor is a constant, so the Cotton tensor is 0, and the Bach tensor is identically satisfied. So theoretically, I would say that if you have solutions of conformal gravity, Einstein spaces are a subset, sort of trivial subset of conformal gravity. What you have to do in order to impose the Einstein condition, you can impose the Einstein condition in many ways, including the fact that you can deal with the traceless Ricci tensor. You can demand that the traceless Ricci tensor is 0 for an Einstein space. And this can be translated into holographic conditions which are more precise than the one that Maldacena was provided. Maldacena was providing this Neumann boundary condition that means that killing higher derivative source. G1 is the source of higher derivative modes in conformal gravity. And G3, of course, because there is no anomaly, necessarily the trace of G3 have to be 0. And G2, because conformal gravity is a higher derivative gravity theory that lives in the Pfefferman-Graham expansion, leaves G2 as a free data. There is no way of fixing that. If you choose by this analysis of asymptotic behavior. Yes. Hello?
Yeah, I think I lost you a little bit, or maybe it's my internet.
Oh, okay.
Okay.
Let me go back.
It's fine. It's fine. I mean, yeah, sorry.
Okay, I was telling that conformal gravity is a higher derivative gravity theory. So in principle, G2 in the Pfefferman-Graham expansion is free data, cannot be fixed. But you can choose it to arrive at the Einstein sector of the theory. You can choose it by the discussion contained in this paper, what is called Penrose-Brown-Hainaut transformations, contained in this paper by Imbimbo, and you choose it as in the Einstein sector as the Schouten tensor of G0. In this way, you are sure that you start from conformal gravity, which is a higher derivative gravity theory, and you kill higher derivative modes, and you end up with a renormalized version of Einstein-AdS gravity. So this slide that I presented, the fact that you started from Weyl squared and you end up with an action that is Weyl squared of Einstein, correspond to passing from a higher derivative gravity theory to a second derivative gravity theory, which is Einstein renormalized. So in this way, there is a relation. Killing higher derivative modes, you can pass from conformal gravity in 4 dimensions to renormalized action in 4 dimensions. So what about 6 dimensions? It's a far more difficult problem. What we have learned this far? We have learned that you need a conformal gravity theory, which contains an Einstein sector. In 6 dimensions, you can deal with 3, depending on the basis that you choose. There is a base in terms of the Weyl tensor. You can propose 3 conformal invariants with arbitrary couplings. But what we have learned from 4 dimensions is the fact that you have to find a conformal gravity which contains an Einstein sector in order to impose the Einstein condition. And luckily for us, there was such gravity theory. It was presented in 2003 by Luke, Pang, and Pope. There is a precise combination between conformal invariance and topological invariance in 6 dimensions in such a way that you can derive the equation of motion, and you can prove explicitly that the Einstein solutions are solutions of conformal gravity. This was not provided in the original paper. I'm not going to provide the equation of motion. You can read in a recent paper, I will list it here. but essentially you derive the equation of motion. They are written in terms of the Weyl, the Cotton, and the Schouten, and you can impose the Einstein condition, and you can prove that generically an Einstein solution is a solution of conformal gravity of Lupin and Pope. And the point is the following: is the fact that they were able to prove that Churchill AdS was a solution. Recently, we pointed out the fact that any Einstein-AdS spacetime is a solution of their gravity conformal. So, what we have a conformal gravity in 6 dimensions, which contains an Einstein sector. So, I have the right to impose in whichever way. I can take holographic conditions, or I can impose the traceless Ricci tensor to be 0, and I can reduce, when I take the Einstein condition in this gravity theory, that once again is a subsector, I can separate the contributions in this gravity theory in the Einstein part and some non-Einstein part. Remember, the H is the traceless Ricci that contains somehow the non-Einstein contribution in the system. And at the end of the day, I can impose Einstein condition, that means H equal to 0, and choose the coupling in such a way it matches the renormalized action of AdS, the Einstein-AdS. Once again, this is a polynomial of the Weyl tensor. It's the polynomial that I was showing you before. That means it's a fancy way of writing down just Einstein-Hilbert plus a topological term, which is the Euler term in 6 dimensions. So what we show is that we start from a particular version of six-dimensional conformal gravity, and we provide we take the Einstein condition and we reduce the system to the renormalized version of Einstein-AdS gravity. That naturally what appears is the renormalization due to the topological term. And if you remember my comment, this is technical but important issue. If you remember my comment that we were able to match the standard counterterms procedure up to certain terms at the boundary that is essentially their Weyl squared terms at the boundary. Here, this prescription provides something even better, because if you reduce conformal gravity to Einstein gravity, it comes naturally with a surface term that cancels this problem that we have. And we have full agreement with the counterterms, with the standard counterterms in the context of holographic renormalization. So maybe this is just to suggest, and I think I will finish with this. This is just to suggest the fact that we were thinking for long that the guiding principle was adding topological terms to the Einstein action. But it's not true. It may be not true. What is the guiding principle is taking conformal structures that contains, that have naturally an Einstein sector and reducing to the Einstein sector within conformal gravity. And this is what your renormalized Einstein-AdS action naturally. Let me see what I'm missing. Yeah, I will
Rodrigo,
jump in the
maybe we can conclude in 2-3 minutes because
yes, definitely.
We can.
This is an old story I'm not going to talk about. We have extensively used these results in the context of computation of holographic entanglement entropy. It's because of this. I will just review this. Let's think of Einstein gravity. Let's go back to Einstein gravity in 4 dimensions. You can define a bare volume on shell. The action is just volume. So it's just a numerical factor of the Einstein action. If you add the chain form, you can think of that like renormalized volume, renormalized action, renormalized volume. And in the mathematical literature, there is such a thing. That means that you are converting the renormalized volume in the Euler characteristic and the Weyl squared term. This already existed in the literature. It's difficult to read this paper, at least for me, and where they point out the fact that the concept of renormalized volume is related to some conformal structures that appears in the bulk. There is a version of the 6-dimensional case that is quite the same as what we found. And so why I'm talking about renormalized volume? Because when you compute holographic entanglement entropy, you go to 2 dimensions lower. So it's renormalization of area in asymptotical AdS spacetime. And we managed to prove that if you renormalize the volume of the ambient space, you may renormalize also the area in codimension 2 with the use of topological terms. And there is a precise prescription that we were working in recent papers. I will jump just to the conclusions. I have reviewed, we have, as I claim, we have started to think that the guiding principle may be the appearance of conformal structures in the bulk. That would provide some renormalized version of Einstein-AdS action. This is interesting because no one knows the general form of conformal gravity in dimensions higher than 8. But at least now we think that we know the Einstein sector of conformal gravity. Maybe whichever conformal gravity you want to construct in higher dimensions will reduce by taking Einstein condition will reduce to expression to the polynomial that we found. So in a way, it could be some hint on what type of structures, at least polynomial of the Weyl to try to find. And this is also what I commented, that the concept of renormalized volume is linked in coordination to the renormalization of the area of the entangling region of in order to compute holographic entropy. Thank you.
Thank you, Rodrigo. It's really a great pleasure to record this talk and where you reviewed your very long body of work on this geometric normalization. So maybe it's time to take questions now. Please ask questions.
So this conformal gravity, it has some, you can't do it beyond this. So the second point that you mentioned, you can't do beyond a certain dimension, right?
Yeah, people have not, I mean, I'm discussing with one of the persons that knows the most about conformal gravity is Nicolas Boulanger from Mons. And I think they were able to generalize conformal gravity with Johanna Ermenger only to 8 dimensions. And they have some clues related to the polynomial contribution, because conformal gravity is you have to consider a certain basis of conformal invariants. And the conformal invariants people may know are the polynomials in the Weyl tensor, but they are, for instance, 6 dimensions. They are polynomials of the Weyl, but there are also 6 derivative terms. And 6 derivative terms come in the combination like cotton square. And this is difficult to guess in higher dimensions. The higher derivative, I mean, the higher derivative terms, they are difficult to guess. The conformal, the ones involving just the Weyl tensor, maybe they will find a way to guess them in any dimension. This, of course, you also touches for instance, the computation of Weyl anomaly also is related to this conformal invariance. And that's the reason why it's so important problem, because we would like to try to identify certain patterns of what is called type B anomaly in holographic computations.
I'm not really following this literature very closely, so my question may be naive, but when you're considering only gravity without any additional matter field right now?
I would say I'm limited to that. I'm limited to that because I have been, of course, it's an open problem, because holographic renormalization also deals with matter fields. And I have not, in all these years, because it is a very old story, in all these years, I have never been able to work out an expression for instance, scalar couplings.
Actually, my question is more specific. I mean, I was wondering whether you can apply it to simpler problem like this of JT gravity, which is in very low dimension, so things are much less complicated, but there is a scalar field to worry about, and then there is a lot of new...
Yeah, of course, you render the theory non-trivial with the use of scalar fields. I'm not able to say anything. I'm trying to depart from pure gravity by very simple setups, because to be honest, I don't understand, because this is a sort of, on the contrary to holographic renormalization, which is a very well defined prescription. It is like an algorithm. This is a non-perturbative proposal. It's like I give you a topological term. Because I like them. The topological terms, I like them, and it's a sort of fundamental. There's not so much room to play with. And for instance, if you incorporate scalar fields, now the question is topological term of which group? Because in this case, they are topological terms of the Lorentz group. They are originally formulated in first order formalism. So you are very much constrained by these observations. If you relax and a couple scalar fields, topological terms of what?
Well, isn't it true that in 2-dimension you also have a large symmetry group and you're not allowing arbitrary scalars? It's just a very specific form of scalar coupling in this JT theories.
I'm not so familiar with, but I would say so. Maybe I should go back to 2 dimensions to try to understand anything at all.
But JT gravity has sort of a trivial renormalization, because it's just simplify multiplying a topological term itself.
Yeah, because otherwise it's trivial, yes. And the Gibbons-Hawking term you construct in the same way, and I guess counterterms you construct later.
The counterterm exactly is simply the topological completion of the So in a way, JT is finite by itself in a way.
So nothing really interesting to be learned in this approach. Is that what you're saying?
In the JT case, yeah, in JT actually.
Maybe one of the things I would like to do, this is related to something that Ian was also doing in 4 dimensions. In 4 dimensions, there are 2 topological terms. There is the Gauss-Bonnet, which is parity even, and there is this Pontryagin, which is non-zero only for instantons or for certain type of perturbations around AdS4, like hydrodynamic perturbations, the way Ian and collaborators were dealing with. So I was thinking of, for instance, relaxing, because I was adding these topological terms with a fixed coupling, once again, to be truly topological. But you can add them with a coupling, with a scalar coupling, and try to see what happens. If you are able to say anything at all about the system.
Okay, Rodrigo, I have one question to ask. So while in conformal gravity in 4D, this paper by I think Boulanger and others, they pointed out something very interesting. I forgot actually the name of the author. Is that it doesn't really require a Gibbons-Hocking like counterterm at all.
Right. Right.
So
there is the holographic version by Grummler and other people.
So my question is
because it's finite.
Exactly. So no, not because it's finite, but it doesn't require any Gibbons-Hocking like counterterm at any surface, even irrespective of. Yeah, I think the point was that the surface term. Yeah, I actually have to remember exactly what was the logic. But is there something similar for 6D, for the 6D theory that you presented?
I think, keep in mind that Gibbons-Hocking terms are a property of second derivative gravity theories. It's in order to Myers' procedure for Lovelock type of terms. Is essentially to eliminate the presence of the acceleration in the Lagrangian. Yeah. So these are higher derivative gravity theories. Is something that you could not the action principle you could not work out so easily. I know the holographic version of Grummler, we were reviewing that in 4 dimensions, and G1 is a new source. But it's difficult to deal with the variational principle in higher derivative gravity theory. You have to use these auxiliary fields and so on.
Yeah, but I understand. But I think the claim of Boulanger, I don't know who, was exactly that the Y-squared term doesn't require any Gibbons-Hocking at all. So there is no need of any Myers counterterm whatsoever. So that was very interesting. Yeah, that was a.
There are recent papers, mathematical, which have pointed out the fact that the fact in the Pfeffer-Lagrange expansion there's a lot of free data, things that remains undetermined.
Could be that comes from
because of higher derivative gravity theory. So in order to make connection with the Einstein sector, we have to choose these coefficients, like in the Einstein version.
Yeah, I'm just saying that maybe because your topological regularization is kind of independent of what boundary condition you're choosing, it's simply a finiteness of the action on shell. So it could be interesting to show that this version that we're getting in conformal gravity, embedding the renormalized action in conformal gravity, that is independent of any the conformal gravity is kind of doesn't require any Gibbons-Hocking like term, which makes it very natural that
yes, because we can discuss this issue later, but actually the additional Gibbons-Hocking term does not solve the Dirichlet problem, or the generalized Gibbons-Hocking, the Myers, does not solve either.
Solve this problem, but in conformal gravity you don't require it at all. I mean, I think at least in the 4D version you don't need it at all.
Yeah, of course, yes.
Yeah, okay, that's okay.
Sorry to interrupt, I'll have to go. So thanks, Rodrigo. It was very nice seeing you again.
Yeah,
and
thank you.
Take care and stay healthy.
But anyway, we are ending now. We are ending now. So let us thank Rodrigo again, and it was a great pleasure to have him.
Thank you very much for the invitation, and I hope to be able to visit you.
Soon. Sure. We are looking forward
as soon as we can. Right? I want to travel
again.
Like crazy. Yes.
Great.
Let's keep in touch and let's discuss these issues.
We will be in touch.
Weeks.
Yeah.
Thank you very much.
Ciao.
Bye. Bye, everybody.